Yeah, if I like it, hey, it's a good opportunity. So the therapist is usually really good for like,
I said he was like the lion or something.
like transferring different branches. Like if I do want to move, yeah, then they can just transfer me to a branch.
Right. That's awesome. I was right. Film.
I kind of want to get out of it. Yeah.
1978.
He doesn't have any excuses.
You're just talking about this.
No,
Never should.
I know you missed me, that's why you're still talking.
Oh, yeah.
Oh, yeah. You saw Abner the invisible dog. Abner, you're invisible. You don't know what I'm talking? With YouTube, Abner the invisible dog. It's the funniest thing you ever saw. Okay, anyway. Okay, homework's at 5 as usual. Yeah, class business. I know it's been a while. That's why I had to ask her to review everything. Sorry, I was in Michigan. Hope she did a good job. A scale of 1 to 10, what would you rate her? Did she really ask that?
Yeah.
So she was, I don't want to do it. I want the other team to do it. And I'm like, I'm going to have you do it because you want to do it. She did anyway. So that's why I had her do a lot of reviews. I know it's been a while. And so she introduced Electrochem. Looked at my notes. We're probably actually on schedule with the calendar if you're keeping up. So that's nice. And I'll have a homework set up late again. Sorry about that. But it's going to be real easy. So here's the big thing about Electrochem is that it's some of the things they're going to go through are like really complicated, but the end is really, really easy. So that's kind of nice. So I'm going to ask you to write out some things like on homework and tests to show me that you understand the underlying complexity, but understand that the answers are going to be shockingly easy to get. So you can easily figure out whether you did the harder parts right. There's a trick to getting all the answers. You do the hard part, and then you do the trick. They're the same. You did it right. It's so freaking easy. This is 3 points. Electrochem is the last of the hard stuff. It's the last bit of delta G's and all that kind of delta G's and everything. But we get to phase changes after this, and oh God, just try not to go to sleep. All right. So we have 3 more extra Fridays. Because this stuff is so freaking simple, it's nothing to talk about, so we read 346, right? The mathematics of 346, which I know, I've done this class before, so we're going to start going over that to get you a leg up, get you ready for that. So I'm sure that's going to help. So, what else? Any other business? I can't think of anything, so any questions? We're okay? Yeah, all right, we're okay. So, all right, Electrochem. Come on, everyone. You're like that right now. So, work with me to survive 50 minutes, 40 minutes, because I've been yakking my ass off. Okay, so, remember that, by the way, for last Monday, I had Azra. Ezra doesn't like being filmed, all right, so I couldn't really ask her to do that, so I posted the notes from last Monday, so that unfortunately, that's just our compromise. So your notes are up there, but remember, so I don't know exactly how she expressed this. We did go over this stuff though, and so remember that this is a phenomenological thing, like PD equals nRT is really just about the same thing. PD equals nRT works pretty freaking well, so there's really nothing wrong with this. Remember that the minus sign gets picked up because Ben Franklin is a jackass. He thought electrons were positive, and actually all conventional circuit design is actually done in reverse because we've held on to that negative sign, that electrons are positive convention ever since he got it wrong. And so like P equals nRT, it's not minus nRT, but here it is because electrons are negative, so we pick up a minus sign. All right, so that was just a thought process. And then we have to do this, minus, I know I did this in reverse, so let me put this out normally expressed. Okay, sorry, remember, number of electrons That's something we'll figure out how to do today. Just Faraday's constant, which just gives me Coulomb times voltage, but we call it E for historical reasons, electromotive force. Okay, this thing, RP, and because all batteries at equilibrium, if this is a K, are dead, because these two cancel each other out, I don't care about a dead battery. And so actually this is something, as we get into this and I start drawing batteries, I'm going to draw different types of batteries. I want you to think about this. Why does a battery die if you never use it? Right? You know, it's true. You find old batteries in their box, and you plug them into your toys when you were little. If they've been around long enough, they are dead. Why? Electrons have never transferred. Or were they? Right? They were never plugged in. Oh, electrons got transferred. You just didn't know how. And then eventually it died. Also think about this. I'll bring this up later. So again, I'm going to ask you why batteries die, even if you never use them, and why when batteries get old and you stick them on your tongue, which you know you did. You did. Hope it wasn't a car battery. When you got little light bulbs and stuck them on your tongue, it really hurt if the battery was new, and it didn't if the battery is old. Was that voltage or current doing that? So that's going to come up. So keep your eyes open. Let's see if you can answer. All right, now we only really care about voltage when it comes to batteries. So we don't care about equilibrium. We only care about voltage. Sorry, I should bring my notes. Minus. Okay, remember Q is the concentrations of stuff that give electrons when the battery is first made. So don't forget that. And this is the standard EMF. So I'm not going to write that down, standard EMF. And those are the kinds of things that we're going to be getting off data tables, just a heads up. And this thing, I'll go ahead and tell you, I'm going to actually, in the future, I'm going to ignore that. I'm going to pretend it's not there, because this is all about how the battery is built. That is in my opinion, is a job for an engineer. Not that I don't appreciate you engineers, but this is an engineering class. I'm not going to try to engineer the battery. I'm just going to try to figure out its voltage. So not that this isn't actually the most important thing about the battery. So let's give an example. Let's say you have a 1 electron reaction. So I'm not going to write all this out. So maybe make some extra notes because I have to do 2 things at once and go. So I have a 1 electron reaction, and the standard delta G is minus 100 kilojoules per mole. Again, sorry, let me back up again. A big picture here is that, again, these are the guys that come in data tables, and then we're going to use those to get these instead of the other way. Just heads up on that. Okay, regardless. All right, so I have a 1 electron reaction, and this is the delta G naught. What is the EMF? That's EMF. So I have a minus sign. All right, minus sign there. All right, then I have a quotient. Minus 100 divided by 1 electron. Okay, I just look up Faraday's constant, and if you need that, and you won't, by the way, but if you need it in the test, I'll have it, of course, in the cheat sheet. Now, of course, a C is a Coulomb. I'm going to write it out because it's probably, confusing right now. I'm trying to figure out how to spell coulombs right now. Coulombs per mole. Okay. Okay, now I can already tell you, I can plug this into my calculator, and it looks like I'm going to get like something like 0.001. But I can also tell you I've just done it wrong. And there's a hint.
Units.
Units, where's the mistake? No, that's what I heard. All right, so no, you got it right, so just spill it. Right. You want joules, not kilojoules. Okay, again, just pointing it out so you don't screw it up. Now, in which case you can see that this is not volts. Basically, it's 1 volt. So that's the definition of the volt. is a reaction that spews electrons with this much energy. That's really a lot, by the way. And actually, your batteries produce several volts. So electrochemical reactions are like strikingly strong. They're like miniature explosions, except that you don't form hot gases. It doesn't literally explode. But some of you also know that batteries explode. It was a problem with the Dreamliner. The batteries kept catching on fire. And that's because these reactions aren't actually, if someone said, oh, a reaction has 100 kilojoules per mole, minus 100 kilojoules per mole, I would say that normally my guess is, the question is, what kind of reaction is that? My best guess is that's an explosive reaction. That's burning octane, that's TNT and oxygen. That would be my guess. And I wouldn't be far off, but in this case, it's for a battery. And also I can see that a volt, what's the unit of a volt? Joules per coulomb, right. 1 over X is X, so I've got moles canceled and I've got a joule per coulomb. So now you know what a volt really is. A volt is not a volt, it's a joule per coulomb. Now, there's a lot of nomenclature I want to show you, and then we're going to start building, I'm going to start drawing batteries, and that I've got two types of reactions that are going to occur. And I'm going to point out a couple of other things. A plus. Okay. Very quickly, I'm sure engineers might know this one. This is what kind of reaction? Reduction here. This is reduction. And oxidation. Okay, I kind of have it stuck in my head now pretty well. The way I remember this is that reduction is bad, and so is becoming negative. All right, kind of sounds silly, but you may get stuck, and that would be bad to lose questions on such an easy thing. Now, here's one of my pet peeves, and write this down because I'm bitter. Hoping to test is that chemistry we have so many words for the. We have one word with multiple definitions, such as oxidation. Oxidation, probably until now, meant you reacted with oxygen, and you would be correct. But we also, because so many things, when they're oxidized, lose electrons, we call this oxidation because it's similar, but it's not necessarily the same. None of our batteries are going to involve oxygen. In fact, there's only one type of battery, the lithium-air battery, that doesn't exist yet, that actually uses oxygen to oxidize. So anyway, we're coming up there. This is actually kind of important when you write out the notation. I'll have it on a homework, but not on a test. You do have to get this straight when you write out the proper notation of the battery, but I will not. I don't see it even on the third test, which is coming up. Well, I think we have about 3 more weeks actually, so we have a fair amount of time. Okay, now I'm going to build a battery. Guys, quick, knock it off here. Just whispers, by the way. I'm hard of hearing, not deaf. All right, so I got a container. It's got a liquid in it. Okay, and I've got 2 metal bars. Here we go, here we go. And I'm building a really bad battery. Just a heads up. That's my drawing skills. Okay, we're going to make this one copper. And we're going to make this one zinc. And I can tell you that the electrons, I hope you can see this. Electrons go from, of course, the battery needs to be wired up. I'll just kind of put a virtual wire in my head. Actually, it's a funny concept. The voltage you measure is called it's an open circuit voltage. And it's kind of funny because to measure voltage, you have to close the circuit. But of course, electronics engineers have very good ways of simulating that and taking that into account. So, and now what we're going to go over is how do you know that electrons go from zinc to copper. And that is, let me write out the reactions first. And then, like I say, a big part of this class is figuring out that the electrons went from zinc to to copper. And this is the correct reaction. Well, these are called half reactions, but again, I'm getting into that in a minute. Okay, and this guy added 2 electrons. Okay, and so copper and zinc are, these are kind of easy to understand, so this is the most common example, and so I'll do that as well. What do I want to say about this? Okay, all right, now for a special reason, so one thing that's happening, all right, so I have wired this up, and it's in my Dreamliner, it's in my Chevy Volt, and what's happening is I have the solution that's engineered to contain copper ions, and so this electrode is building up. This is how you electroplate, by the way, and this electrode is slowly dissolving. It will eventually corrode completely, and the battery is dead. All right, but I can tell you that this is a horrible battery. This is the worst battery in the world. Maybe not quite the worst battery. I'll design a worse battery than this in just a moment. I can tell you this is not the kind of battery you use. Why is that? Remember, it's in salt water. I've got these 2 little wires, lots of electrons exchanging in salt water. What's wrong? It's a short. Yes, it's short-circuited. This does not work. Sorry, it does work. It's just all the electrochemistry doesn't go through a wire. It goes through solution because that's easier. Also, okay, well, I didn't add wire. It's a battery sitting in my drawer. Yeah, maybe by tomorrow it's dead. So this is not a good battery. Okay, now, here's the question. I'll put a little partition in between there. I'll build a wall. This is how anal I am. I'll build a little wall between them. Okay, I guess I should do this as well. Okay, I built a little wall. Now, this is actually a worse battery. Because when I wire this up, it's not going to last long. Why? Yes, there you go. Charge builds up. So, yeah, I mean, if all these electrons are going here, in this case, if this is a wall, then this is becoming highly negatively charged, and this is becoming highly positively charged. So the easy thing to think about if I ask this question on a test is electrons are going to a sea of electrons, and electrons repel each other. And get that gets confusing. You all played with magnets as a kid, and north, it's just like that. Magnets are how you make electrons. And now also think about this, the electron, let's just say that for magic reasons that wasn't true. The electron, as it leaves, is having something pull on it. So there's something blocking it, and then there's someone else holding it back. So between the two, this battery would run for about a second. So no good. So now what you do is you make this partition ion permeable. Okay, so what happens is, I painted myself into a corner. Hold on, let me make sure I get this right too, because I really struggle with electrochem, by the way. Yeah. Okay, so I hope you're not having trouble seeing this. I'm sorry about this, but negative ions go this way, and positive ions, oh God, this is awful, I'm sorry about this. Positive ions go that way, through the membrane. So one of the things that people just never really think about is, you look at the battery, you're like, oh yeah, what happens is you put little wires to these guys, and electrons flow. And that's all that happens because that's all you care about. That doesn't work because of the charge buildup. You have to compensate inside the battery. So there's stuff moving inside the battery. Not snakes, but little ions. So this is a functioning battery, but it's not still a good battery for a weird reason. And that is the ion permeable partition doesn't work really well. When we build, we have lots of ion permeable types of films. Biology, your cells are actually just like that. They tend to work for one type of ion and not the other. So in other words, it's really good about letting the positive but not the negative pass. That's no good. Again, from an engineering standpoint. if the one ion moving does compensate, but then you're losing half your oomph, because then the negative doesn't pass, or vice versa. So again, finally, a functioning battery, but still a crappy, crappy one. So that's where, I'll draw this bigger because I look like I screwed that up pretty good. That's where I know you learned this in freshman. I was always bored to tears with this stuff personally. Of course, you know, I'm pretty bad about disparaging my own work, regardless. So work with me. I know this is a lot of drawing and it's kind of boring, but that's what we got. So here is, you already know what I'm talking about. It's the salt bridge thing. But this salt bridge, of course, does a lot. Here's the other electrode. And again, we'll just do copper zinc. Sorry, I'm usually a bit better drawer than this, but here we go. And of course, there's still the solution. Here. And of course, this is still Cu. This is, see, I could have saved my little drawing last time had I done it this way. And this, of course, is the salt bridge. And of course, electrons are still going this way. But don't write that down. We already know that. Okay, so remember that metal bars, sorry, see I got out of practice this single week, are the electrodes, again just basic battery design. Let's see, the anode is where oxidation is happening, the cathode, I tell you, I never keep this straight. This is the reduction side. All right, so if I'm oxidizing, this is what always confuses me. Oxidation is when something becomes positively charged. So I think of that as not the source but the drain, where the electrons go. Meaning I'm wrong. If something's being oxidized, it's generating electrons. Okay, so it generates electrons. So anyway, that's my hang up. Don't try to memorize what I just said because it's wrong. All right, but what is right is that oxidation, if something's being oxidized, that means it's shedding electrons, so that's the source. And therefore, the reduction side is the ground. It's often called the same, but it's really the same thing as like a grounding wire. It's where the electrons will go. And for those of you who I don't know if you engineers have covered this stuff, but if I open up the light switch, there's a white wire and a black wire. Which one is the death wire? I just pointed to it, didn't I? Oh, yeah, black wire, right? Yes, the black wire. So when you're messing with circuitry, fear the black wire, by the way. Or maybe don't do it. That would actually be much smarter. And now the purpose of the salt bridge, there's a subtlety to this. Let me tell you about the subtlety, but then let me tell you what's really going on. Okay, so this guy is generating, this solution is becoming positively charged, and this solution is becoming negatively charged, right? And the whole point of the salt bridge is to fight that. If I haven't been here, again, these are electrolytic solutions full of ions, because I have to have ions flow. And in terms of the salt bridge, you could actually still fill this with fluid. That's usually some kind of jelly type substance. And you see what happens with almost any kind of, I notice these are touching each other, but reality is things don't move that quickly. So when this whole solution becomes positive, because the electron's left, you're actually going to pick up a little bit of a negative response to that, because when something's happening, it's not in equilibrium. And so at equilibrium, nothing is charged. But when I'm using the battery for its purpose, I know that this is building up charge. And this guy's going to turn a little negative in response to that. Like how north to north on our magnets, one of them will flip, right, if you let it. So that's actually happening here. And it's happening because we're not really in equilibrium. And this part, of course, does the exact opposite. It builds up a little positive charge there. The point of this is people often say, well, this is what makes a salt bridge effective. And they just kind of leave it at that. But reality is, how is this different than when I had no partition here, right? Remember, this was the battery that dies really quickly, no partition. The electrodes are touching each other. Well, electrode, solution all the way. So why the hell is this effective at all? Well, let me real quick. Now let's think about an electron coming from here to here on its own, no wire, right? And that's what we don't want. Sorry. Back up. It's not hooked in, right? It's sitting in the shell. I don't want it to die. I want electrons ultimately to go this way, not this way. All right, an electron, when it's turned off, is kind of attracted to this positive charge, but it won't flow because it runs into a barrier. So that helps the electron not flow. But it does anyway. So it goes this way and it sees that positive thing, which helps it, but then it runs into another barrier. It kind of just impedes the electrons from going from one side to the other. Now, some of you knew what the black wire was. Impedance is a fancier word for what in electronics? Resistance. All the salt bridge does is it increases the resistance between the two electrodes, so electrons don't flow. Right? You know that's how these things work. A big metal bar has no resistance, and a plastic one has a lot. Now, note you can't also get rid of the resistance either. It can't be zero. That's when you put a real block. You put a real block, and that doesn't work either. The whole purpose of this is to kind of meet it halfway. To increase that resistance really freaking high, but not to totally get rid of it, because if you did, the ions couldn't flow, and then you wouldn't get rid of your charge balance. And there you go. That's really about all the issues with battery design. They got to touch, but through high resistance until you plug it into something. The second issue is charges unbalanced here, so they have to rebalance there. So a lot goes on inside the battery. When we go over lithium-ion batteries, I'll explain a little bit more. This is a little overly simplistic when we talk about lithium-ion batteries, because those are awesome. I'll tell you a little bit more about how difficult they are to engineer, but of course we all know we want them. And, last question. Battery is new and it touches your tongue, and it hurt, and then the battery got old, and this actually has more to do with this. The battery got old and it still stings, but it doesn't hurt as bad. Is it current flow or is it voltage that went down? Obviously something was reduced. Was the voltage of that battery decreased because it got old and used? Voltage. I heard one of you say kitties. The predominant answer was current, and that is yes, correct. Right. So remember, right? This is the voltage, and this is the ions eventually in the battery. This is the electrodes wasting away. This part. Eventually, the electrodes are complete. This guy's gone, and this guy's corroded beyond belief. At that point, this thing kills that thing. So what you're really changing is the total current that can flow, but not the voltage. Kind of. The voltage is kind of changed for weird engineering reasons, but for the most part, that's really the problem. So anyway, kind of an interesting little thing about batteries. So I think you've already had all this probably in freshmen. I mean, I remember having this in freshmen. So hopefully, when we get to lithium-ion batteries, which are pretty awesome, I'll show you a little bit more about advanced battery design. That's pretty interesting. We actually just hired a guy who does nothing but design the interior, the chemical interior of lithium-ion batteries. And the thing is that there are solids inside of it. I mean, I just drew the thing with some bars that are on the top of the battery and some liquids inside of it, maybe a little jello. But in a lithium-ion battery, the interior are made of solids. So how does that work? How do ions flow inside of a solid? Until then, I have to go over this other crap. Notation. my ox, because I like oxen, is red. Okay, so when we write out chemical reactions, guess which one we start with? I write oxidation to reduction, and okay, yeah, we can see that up here. And so, what's being oxidized? What's becoming charged? What's becoming? Zinc, right? Zinc is becoming oxidized because it's the one that's dissolving, and as it dissolves, right? So that's the anode. As it dissolves, it's also the black wire. That's the death wire, the power wire. And so, the way you do that is the idea is that in the notation, a vertical bar represents a phase change. It's a little stupid, but so the way you write this is Zn bar, that's Zn metal, and it's going to become a Zn salt. And Zn salt, we're going from solid to aqueous. So Zn, now I don't care if you were to write 2+, but that's not so standard. Often you give it the counter ion. So remember, of course, that zinc dissolves. The whole point of the whole salt bridge and all the electrolytic solutions is to have a bunch of ions. Because I can't ever, this is kind of a funny thing. Can you just take water and add something such that there's only positive ions with no negative ones? Is that possible? Think about it. What if I just throw in sodium? Don't I get a bunch of Na+? Huh? Yeah. I get NaOH. I get Na plus OH minus. Right, so you can't really just insert one type of ion into solution. I guess you could do a limited extent if you could like build a machine that would shoot positive ions, but eventually the solution would actually deflect any kind of thing like that you were doing. So I don't care if you write Zn 2+, but if you want to be technical, you would put down a counter ion. Now, any of you know what's in a lead acid battery? We don't really use those so much anymore in cars, but when I was your age, most car batteries were lead. Are they still actually lead acid? No. Anyway, back in the day of lead acid batteries, guess what the acid was? Right. I might have accidentally given away the answer. All right, so, 2 ways of doing that. Now, the salt bridge is 2 double lines. What's being reduced? Copper. All right, now, you got to be careful about which way you write it. So, if I am making more copper metal, and this is called, by the way, this part is called a half reaction. I need to start with the ion, and that's in solution, then it turns to copper. And there you go. So that's the notation. I may ask this on a homework question, but I'm not going to want to tell you that I just don't do it now. And what can I do is I can give you this and say, tell me what the reactions are. And again, so why am I doing this at all? Because it could be on a standardized test. Okay, so I've given you the above, and you should be able to write out the fact that zinc is being oxidized and copper is the guy taking the electrons. Sorry, I'm trying to make the little arrows line up and then kind of angle as well. Okay, last bit before we actually calculate stuff that matters. And by the way, I have all your homework. So another battery here. So same old. Another little guy here. I'm going to build a salt bridge. So I just want to show a different type of battery, even though the diagram is pretty much identical. I should just write over my old one, but I think we'll drive them nuts when I do that. I kind of hate doing this stuff. There we go. That's awful. Go. And more solutions, whatever. Now here's the neat thing, is that the number of materials you can use to participate in a battery. I already mentioned, all right, so I've got my sulfuric acid, copper, and zinc. I've already told you that lithium-ion batteries are almost all solid or almost all solid. but you can get gases too. So remember, these are electrodes. What you can do is you can use gases as well. You can have H2 going into solution. And there will be some kind of equilibrium process, of course, so I'll do it this way. I can't say which one's going to go which way yet. Go. Yeah, you can just watch the video on this if you don't want to draw all this out. That's probably what I would do. So you can use gases too. And the net reaction is H2, HCl. Now my stoichiometry is bad, but I don't think that really matters. Maybe I'm not right. Maybe I should be writing 2HCl, I'm not sure. Okay, and so again, solids and liquids and gases can all be used to make batteries. This was important because this is the standard hydrogen electrode. Okay, so now remember what this is leading up to, which I'm going to start talking about right now, and just touch on it a little bit because I'm going to get back to your old homework, is that we ultimately are going to want to get those delta G's in the table in the back of the book for like ions. And the thing that's not an ion. And we're going to want to build that table up again so that we can calculate all the voltages of a reaction. And then of course we add and subtract just like we did. It just Hess's law, it's a little funkier. All right, so to get those voltages that we want to know as the battery operates, we're going to do Hess's law, and we're going to have a table in the back of the book with delta G's, but we chose not to do that. Instead of measuring delta G's, which is perfectly feasible, we decided instead to measure EMFs instead of that. And of course we had to have a reference state, a reference electrode. So this thing, it kind of makes sense. We make this thing, we hook it up to another battery, the one we actually care about, and we measure the voltage. And then we assign that voltage to only that other thing that I'm not drawing here, that I wire up in some way. And then I make a table in the back of the book, and I add every ion possible that I can make these bars out of. And then, there you go, there's your table. And then you do Hess's law, and you get everything right. You know what your standard EMFs are. Okay, so now let me start writing the standard EMFs. So again, this is the part where this actually starts to look like it's really hard. It's not too bad. I think what you did on the last homework was much harder. And so it still looks a little painful. But then, it's like I say, there's an incredibly easy trick to all of this. And so I'm going to ask you, I'm going to say, tell me what's going on, give me the answer the hard way, and feel free to check it the easy way. So, hard questions that always know the answer are pretty nice questions. So, delta G, delta reaction G, and this is why I should PowerPoint. Let me point out, okay, let me go back a little bit, and I should do my notes a little bit better than this. Sorry, I'm being an idiot. I'm really not doing this the right way. Sorry about this. Let me start over so that this is a little bit more clear. Just looking at my notes now, and I realize I could make this really a lot more clear. First reaction G. E is E0. I'm just going back to the notes to minus 1. And this is equal to okay. Where this guy is sorry, I'm going to take it to these right now. Minus not over VF. Okay, sorry, I'm just looking at my notes and I realized I just got it in my head there's a better way to explain this. Okay, so what I'm going to do now is, this is the voltage I'm going to measure, right? And this is the voltage from the table in the back of the book. But just like I had to do then, I have to do now, I have to take into account how things mixed and how entropically things change. I know it's entropic because there's a natural law. Just like how gases wanted to mix halfway, but then delta H also drives things. So the mixing part's right here, but you know what? Again, I don't care how the ions mix. I don't care how the thing moves into the future. I like fresh batteries. So I'm going to say this is 0. So forget about it. So what I'm going to do is I'm going to relate the voltage to just this. And why? Now remember a long time ago I mentioned that the activities of solids were always 1. And remember that this is a little function of the activity. So a lot of the components of a battery are solids. So a lot of the components of Q are already 1, and I'm going to take the natural log of 1, which is going to be 0. Now a battery, except in a couple of cases like a lithium air, well even in that case you have air, there's really no such thing as a battery that's composed completely of solids. They're mostly solids. They might have to have a liquid salt bridge, and they have sulfate ions and sulfuric acid, that's in there. But this is all engineering. It's all battery design. And I can design a battery such that this is 0, such that Q is 1 and Ln of 1 is 0. So look, it's there, but I don't want to spend a lot of time on this because it's all a matter of engineering a better battery, and it just doesn't add anything to your understanding, it just complicates it. I don't care about complicating things if I can just make it 0, which it really isn't that bad an approximation, and still you get how this works. That's much more important. If you want to know how this thing works, then take the class on batteries, which I'm teaching next semester. I'm kidding. Anyway, so let me get back to my notes. Okay, now the whole point of this is, I mentioned before how zinc and copper do what they do. Well, how did I know what they did? So I'm going to write, these are called half reactions, and we always write them as reductions. So I always bear writing down reductions. So many of you know, he did have this in freshman, I know this 4 years ago, or a little longer for some of you, that the table in the back of the book are half reduction reactions. And they look like this. So anyway, I know if I'm reducing, I've got, I may forget this AE stuff in here. 2 electrons goes to solid copper. Of course, all solid metals have an oxidation state of 0, because otherwise that's a metal bar with a lot of positive or negative charge, which doesn't make sense. And I recognize your voice, by the way. Well, I got to know you. Isn't that horrible? Anyway. Okay, there we go. Solid. Now what you've got are the EMFs, which are in voltages. And what you get in this case is 0.34 and minus 0.76. And let me, sorry this got ugly, I just should have done it, should have had this in my notes. Okay, now, which ion likes to accept electrons? Now, I know that means a negative delta G. That's one. Both of them? Now, remember, I can look at this, and I see one's positive and one's negative. Now, remember, a negative delta G is good. So it makes me want to make this one because it's negative. It's a positive one because of the negative sign. Thank you, Ben Franklin. And Franklin wasn't such a screw-up, that would be positive, and these would be flipped. And then it would actually make more sense. So because of that, we don't go with the negative EMF like we would normally go with the negative delta G as being favorable. Instead, it's a positive EMF. I just hate. Sorry, I can't get over Princeton. He didn't let his daughter marry the man she loved. He cut his kids off in his will. Yeah, God, you know, you should see what I did. It was great. I tried to dig him up. Law enforcement, that's not a confession. So, okay, so what I get from that is copper loves electrons. It wants to eat electrons, and zinc loves to shed electrons. So that's what I get from that, and that's how I knew that the zinc would dissolve, because this is a negative, positive delta G, which is bad. So, God, that's confusing. This is a positive delta G forming zinc metal. So zinc metal wants to go the other way. It wants to dissolve and give off electrons, and copper from solution wants to plate out and form solid copper. That's how you do copper plating. Let me also go over one last bit, and then we'll end there. God, this is so boring at times, but there are standard conditions. So when you measure EMFs, there are standard conditions, and what that is you're going to have 1 mole of X. That's like copper or zinc and zinc ions. And, well, there's no such thing as, anyway, so you'll have 1 mole of copper, zinc ions, that would actually be ions, I think, in a cell. And then you have plus 1 mole of HCl, because this is the standard hydrogen electrode, so they're open to the air. This is this guy here with 1 bar H2 gas. So I take this thing, I build that battery up there, I take the tops off, and I put it in a box that's under 1 bar pressure hydrogen. The solution has 1 mole of HCl, and then I've got 1 mole of copper and zinc solutions in the cells, and I've also got their corresponding 1 mole of ions, whatever those are, and then the temperature at 298. 98K, and that's where we come from. Okay, since that's as far as I can really go right now, I'm going to come back to homework. What I'm going to do then is use these EMFs, translate them to delta Gs, figure out how I get the most negative delta G that gives me the reaction, take the new G, put it back in here, and get the voltage. That's the strategy for calculating voltages. Homework will be up later. Easy. Please pick up your homework right here.